Hi, my name is Guangyao Shi. In this video, I will present our work on multiple path orienteering problem under adversarial settings. This is a joint work with Li Feng from Orienteering and my advisor Pratap. In this work, we consider the scenario where robots plan paths to collect rewards, for example, the samples of the environment. Each robot needs to satisfy some budget constraints, which may relate to the battery of the robots or the requirement of the task. This is a basic setting for the team orienteering problem. In this work, we further consider the possibilities that robot can fail or be attacked. So the problem we consider is how to maximize the collected rewards by the team under some adversarial cases. This work is related to two lines of work. One line of work is on submodular team orienteering problem. Such a problem can be used to model many multi-robot tasks, including the exploration, coverage, and informative path planning. But this problem cannot model the adversarial cases. And another line of related work is on robust submodular maximization. But existing works deals with set elements, not paths for the robot. Here are some assumptions we made for this work. The first is that the environment is discretized into a graph and the reward function for each robot is submodular. The second one is that we assume at most alpha out of n robots will be attacked or fail, and the alpha is assumed to be known. Mathematically, the robust multiple path orienteering problem can be modeled as a maximum optimization of a submodular function f. Here, function f is the reward function of the team, and we can construct this function from the reward function of a single robot. And here, S is the set of paths for all robots, and we need to construct paths for the robots in a one-by-one fashion. And the set A here is the set of paths that will be removed from the set S. In this optimization problem, the first constraint corresponds to the limited number of failures or attacks, and we assume alpha is known. And the second constraint corresponds to the number of robots, cardinality constraints. And the third constraint corresponds to the budget constraint for each robot. One contribution of this work is that we give a bounded approximation algorithm for our MOP. The algorithm works as follows. First, the algorithm will let the n robots to solve our orienteering problem independently using some bounded approximation algorithm. Next step, the algorithm will choose alpha best out of n paths constructed. For the rest of the n minus alpha robots, we will use sequential greedy assignment to construct paths for them. Here, the sequential greedy assignment means that we first construct a path for one robot and set the rewards of visited nodes to be 0, and then construct a path for the second one. Such a process repeats until all the n minus alpha robots are given a path. The challenge of such a process is that the orienteering problem is NP-hard and it can be only solved approximately. Despite of the hardness of the proposed problem, we show in this work that given some bounded eta approximation algorithm for orienteering problem, our algorithm has a constant lower bound, which is a function of eta and the curvature of the function. Here is one intuitive explanation of our algorithm. In the map, different colors of nodes corresponds to different rewards. The closer the color to yellow, the higher the reward of the node. In this example, we have 6 robots in total, and we assume at most 3 of them will fail. On the bottom left, if we use the sequential greedy assignment for the team, and we don't consider any possible failures, when the worst case attack happens, as we can see here, we will lose paths on all the important nodes. By contrast, if we use our algorithm, there will be some overlaps over the important areas. So when the worst case attack happens, we can still preserve some important nodes. Thank you for your attention.